So to recap this and to use some animation and some diagrams to solidify the point, we'll start with a simple block of flash with 9 single level cells. And remember, right, this is an oversimplified example for demonstration purposes only, so bear with me because I think it does work for demonstration. This flash block is fresh out of the box, meaning that all bits are set to 1s. We can see that in the diagram. And remember, when flash memory is in a fresh out of the box state, you can individually program any cell at the cell level to be a 0. So let's change the values of 3 of our flash cells in this block to be 0s. Great stuff so far. All of this is real easy for the flash controller. However, let's make things a little more difficult. Let's say we want to reprogram the cell in the bottom right hand corner from a 0 back to being a 1. Uh-oh, this is where it gets hard. Remember that as soon as you want to program any of these 0s back to being 1s, you have to perform an erase operation known as a block erase. And this is quite intensive for the flash controller. First of all, the flash controller is required to read into memory. Oh, and by the way, all flash controllers come with an amount of onboard DRAM for metadata operations and other operations such as this. So the flash controller has to read the entire contents of the block into its DRAM memory. Next, it has to compute the new contents into DRAM. Here we can see the final 0 has been changed to a 1. Next, it performs the block erase operation, which incidentally is apparently where flash memory got its name from, hence the picture of a flash on the slide. This block erase operation returns the contents of the entire block to the fresh out of box state, that is, all 1s. And then finally, after all of this effort, can that tiny little single cell in the bottom right hand corner of our flash block be changed from a 0 to a 1. Talk about a lot of hard work and effort just to change one cell. Wow, I feel like I need a rest after that. What we've just described here is often referred to as write amplification. Write amplification is basically any time that the number of write operations performed by the storage device is more than the number of write operations performed by the host or application. It can also refer to the size of the write operation performed by the storage device being larger than the size of the write issued by the host or application. This is clearly the case here, as the host only wanted to update a single bit in a single cell, whereas the device had to write out the entire block. And this is also without considering all of the complexities that went with the process. Net result, write amplification sucks and drags performance into the gutter. The net result of all of that being, flash memory isn't as good or as fast at writing as it is for reading, especially when it's not in a fresh out of the box condition. And let's face it, in a busy environment where your flash memory is highly utilized, it's rarely going to be in that fresh out of box condition. So you need to be careful and understand fully that flash memory will perform far better at writes in a fresh out of box condition than it will do after several hours of intensive use. Okay, so let's take a look at some tricks that some of the flash vendors and the flash technologies have up their sleeves to improve performance and the availability of flash.